Greetings and welcome to the 21st clinic in linear algebra. Today's clinic is going to focus on problems dealing with eigenvalues, eigenvectors, and eigenspaces. All right, so first thing we're asked to do is find the characteristic polynomial of this 4x4 matrix. So you should recall that the characteristic polynomial of a matrix is the determinant of lambda I minus the matrix. Right? Where lambda is just some constant, I is the appropriate identity matrix, yeah, and then of course A is our matrix, right? So we're looking for, let's actually go ahead and move this down a little bit, give us a little bit more room. So there is the determinant we want, right? And when you take the determinant, right, what you find is this. So there is our characteristic polynomial. Now we want to find the characteristic polynomial of this 4x4. Right, so again, we just want the determinant of lambda I now minus b. Right now, since this is a diagonal matrix, the determinant is very simple. Right, it's just the product of the diagonal elements. Right, so when you do that, this is what we're left with. Okay. Go. All right, so now what we're going to do is go ahead and find eigenvalues, right, and the corresponding eigenspaces, and we will then also determine a basis for each eigenspace. So eigenvalues are the zeros, the roots of the characteristic polynomial, right? So the first thing we want to do is find the characteristic polynomial. So we're going to need to take the determinant of lambda minus 3, 4, negative 2, and lambda plus 6. All right, and we get as our determinant lambda squared plus 3 lambda minus 10, set that equal to 0. All right, what we get is eigenvalues of minus 5 and 2. Right, so each eigenvalue has an associated eigenspace. So let's start with the eigenvalue negative 5. We want to determine its eigenspace. Well, all we have to do is plug negative 5 in to lambda I minus a, right? So we're going to plug it in up here, except we're not taking the determinant. We just want the matrix. And we get the matrix negative 8, 4, negative 2, and 1. All right, now let's go ahead and reduce this. And so you should see that from this, we get a system of equations. Specifically, let's call it x1 minus a half x2 is equal to 0, which means that x1 is equal to a half of x2. So our first eigenspace, okay, is the set of all vectors of the form. We could let x2 be r, right? Any real number. But let's avoid fractions. Let's call it 2r, which would make x1 r. Okay, so there's the eigenspace and a basis for this eigenspace. Okay, just set r equal to, I need to specify. No, r can be 0. That's fine. It has to be 0, in fact, actually, right? Because it has to contain the 0 vector. So a basis, right? Just set r equal to 1. So there'd be a basis for this eigenspace, okay? Now, don't have to let r be 1, right? We could have said r is 8, and that would have been a basis, right? So we want an eigenvector. And the eigenvector is any element in there where r is not 0. Okay, so that was for the first eigenvalue. Now we need to do the same thing for the other eigenvalue, which was 2, right? And the process is identical. Right, so we first replace lambda with 2. Now RREF it. This means, of course, x1 is equal to 4x2. So our second eigenspace, set of all vectors of the form 4r r, where r can be any real number. And then a basis for this eigenspace, we can just say r is 1. And there you have it. Okay, so let's look at 2213 now. Okay, so again, we want the determinant, lambda minus 2, -2, -1, lambda minus 3. So that gives us lambda squared minus 5 lambda plus 4. Set that equal to 0. And we get that lambda is either 1 or 4. So two eigenvalues, 1 and 4. Okay, for lambda equal to 1. Right, we'll reduce that. We get 1, 2, 0, 0. This means, of course, that x1 is equal to -2x2. So the eigenspace associated with this eigenvalue is the set of all vectors, -2r r, such that r is any real number. Which means a basis for this eigenspace would just be the set of the vector -2, 1. Right, now do the same thing for the eigenvalue 4. Right, if we plug 4 back in, we're going to get the matrix 2, -2, -1, 1, where it reduces to 1, -1, 0, 0. In this case, x1 equals x2. So our eigenspace, set of all vectors of the form RR, such that R is any real number. And we get as our basis 1, 1, set 1, 1. Well, let's tackle a 3x3 matrix now. So we're going to take the determinant of this matrix. We get lambda cubed minus 11 lambda squared plus 39 lambda minus 45. Set that equal to 0. We get that lambda is in the set 3, 5. So we have two eigenvalues, 3 and 5. Right, so let's tackle the first eigenvalue. We'll reduce this. So this means, of course, that x1 is equal to negative x2 plus x3. Right, so our eigenspace, set of all vectors of the form negative r plus s, rs, such that both r and s are real numbers. So to form a basis, let r be 1 and s be 0. Now let s be 1 and r be 0. So there is a basis for this eigenspace. Now we want to work with the eigenvalue 5. Okay, so we get this matrix, row reduce it. Right, this leads to x1 equal to x3, x2 equal to 2x3. So the eigenspace here, instead of all three vectors of the form r, 2r, r, right, for any real number r. And so our basis is the set of the vector 1, 2, 1. And finally, we're going to look at another 3 by 3 matrix. Okay, so we want this determinant, get lambda cubed minus 12 lambda plus 16, set that equal to 0. So we get for our eigenvalues negative 4 and 2. For lambda equal to negative 4, This will reduce to this matrix. All right, so this means that x1 has to be 0. x2 is x3. Right? And so we get, as our eigenspace, the set of 3 vectors of the form 0, RR, right, for every real number R. This makes our basis. I should say makes a basis, the set 0, 1, 1. Now finally, for the eigenvalue 2, right, we'll reduce this. This gives x1 equal to x2, and x3 has to be 0. So our eigenspace set of all vectors are 0 for every real number R. And so a basis be the set of the vector 1, 1, 0. The next clinic will be the final clinic of the semester. It will deal with the diagonalization of square matrices. I thank everyone for attending. Thank you so much for watching. See you next time.